we are able to walk and run due to static friction. Here is a problem based on this. Mu is given 0.9. "50-meter distance has to be covered. What minimum time is possible?" Minimum time possible means there should be maximum acceleration. The only force acting in the forward direction is static friction. When you walk, you push the ground back, ground pushes you forward. There is no rubbing taking place, so it has to be static friction. For acceleration to be maximum, frictional force should be maximum. And we know that the maximum value of static friction is mu times normal reaction. Because there is vertical equilibrium, normal reaction should be equal to mg. So the maximum friction will be mu times mg. That friction mu mg will provide acceleration. So it will be equal to ma. That means A is equal to mu g. Mu is 0.9. Take g as 10. 9 meter per second square is the maximum acceleration possible. So a human may have, a Superman may have tremendous capability, but even he can do nothing about it. Acceleration cannot be more than 9 meter per second square. He can do nothing about it. If he is wearing those shoes, that's the maximum. Yes, he can fly, but the question is not based on that. Now, find the minimum time. So we want time. Which formula should we use? find time. Starting from rest, so u is
So
0.
you can use
Which one?
either of the first two, v is equal to u plus 80 or s is equal to ut plus half 80 square.
S equal to ut plus half 80 square.
Or half 80 square simply because u is 0.
Let's try this. S equal to ut plus half 80 square. So S is 50. U is 0. Half 80 square. A is 9. Can you find T? Can you find T? And see
So
if you...
10 by 3.
10 by 3. So you're getting 10 by 3. So S is 50, U is 0, plus half into 9 into T square. So that should get you T as 10 by 3. Any questions regarding part A? Let me know. Then let's look at part B. Suppose he takes exactly this much time to complete this 50-meter distance. What minimum time will he take to stop? Well, how are you able to stop when you are running? I think I gave you one question which had to do with some snake coming in front and suddenly you stop. So who stops you? You're running or walking quickly when you see the snake and you stop. And the answer is, it is the ground that stops you. Now you can answer it a little bit better. You can say that it is a static friction that stops you. And in this part B, we want minimum time it should take to stop. So that means maximum deceleration we want. Maximum deceleration. Maximum deceleration will come if there is maximum static frictional force. Maximum static frictional force is mu n. And n will be mg due to vertical equilibrium. So it looks like the same type of thing. F will be equal to mu mg only, and mu mg will be equal to ma. Same story. So acceleration plus 9 or minus 9, maximum will be this much only, 9. Right? So maximum deceleration will be 9 only. So now you know deceleration is 9. Can you find out what minimum time will he take to stop?
So it would be the same, 10 by 3 seconds. In this case,
It has to be the
would be
same.
30 meters per second.
U is 30. Yes. U should be 30. For part B, U should be 30. So if you have any problem, let me know. For part B, U should be 30 and A should be -9. And T should be 10/3. Any questions? Let me know. Let me ask you one thing. For this journey, what will be the direction of frictional force? Left or right? For part B, what is the direction of frictional force? Right or left?
It's a left.
Left. That's why we have taken acceleration -9. And for part A, 0 to Vmax, what is the direction of frictional force?
It's a left only.
If frictional force is left, then how is Superman going to the right? When you walk forward, what is the direction of frictional force? Forward or backward? When you walk forward, is frictional force forward or backward?
Yeah, forward.
Forward. It is because of frictional force that you are moving forward. So frictional force has to be in forward direction. When a block slides in forward direction, then what is the direction of frictional force? When a block slides in forward direction, what is the direction of frictional force?
Sir, it should be backwards.
It should be backwards. And which type of friction is this?
It's a kinetic.
Kinetic. And when a man moves forward, then which type of friction is it?
So static friction. Static.
Static friction. So see the interesting difference. Block slides forward. Kinetic friction acts backwards. I'm talking about sliding on floor, that type of case. Friction acts backwards, kinetic. On the same floor, a man walks forward. Static friction also acts in forward direction. That is because when a block slides, block does not walk. Walking is a different type of thing. You tangentially apply force in backward direction. When you walk forward, you are tangentially applying force in backward direction. And that is why static friction is acting in the forward direction. When block slides, it doesn't apply force like that. It just slides. And static and kinetic friction doesn't want it to slide. It wants to stop it. Okay. Any questions, or we move forward? I hope nobody has problem with Vmax. Initially, when Superman is running 50 meters, then he is accelerating. So his speed becomes maximum when he reaches this 50-meter mark. So when he reaches this mark, I have called that speed as Vmax. So Vmax is 0u plus a9 into time. Time we already found 10 by 3. 30. And that Vmax becomes initial speed for this journey, which is a decelerating type of case. When you try to stop, and when you are running and you are trying to stop, then you again apply force on the ground, but you do it in a different way now. So it is you who is actually controlling it. How ground should apply force on you, that you are controlling. This problem goes like this. You can see an inclined plane, angle is 30 degrees. There are different friction coefficients as far as the two blocks are concerned. Mu1 for this, mu2 for this. This is 2 kg block, this is 4 kg block. We want acceleration of 2 kg block under two different conditions. Under two different conditions. First condition, if mu1 is this much, mu2 is this much. Second condition, given. Now, what is the basic idea in this problem? The basic idea is that, will they go together or will they not go together? Or will they go at all? That is another question. Will they go at all? Or they will just stay there? If you consider some block alone on an inclined plane, then this is the formula for acceleration. Which means that if sine theta is more than mu cos theta, then the block will accelerate. This will become non-zero. In other words, if tan theta is more than mu, then the block will accelerate. If tan theta is more than mu. Ten 30. (1.7/3). Let's say nearly 0.6. It is much more than mu values. There is no reason for anybody to be at rest. They should be moving for sure. But will they move together, or 4 kg block will go too quickly, 2 kg block will go too slowly, so they will separate from each other. You can see that if mu is less, acceleration is more. If mu is less, acceleration is more for an isolated block. If mu is less, acceleration is more. Mu1 is less, 0.2. So the rear block should try to accelerate quickly, and the front block should try to accelerate slowly. It's like a sluggish man in front and a smart man behind. Smart man tries to go quickly, sluggish fellow doesn't let him go quickly. So what choice do they have? Both will have to go together. No other choice. So while 2 kg block wants to go quickly, but 4 kg block doesn't allow 2 kg block to go that quickly. So they will have to go together in that case. 2 kg will continuously try to push 4 kg. We are assuming one dimension, one line type of motion. So ignore this type of situation. Ignore this type of situation. If it's a plane, well, it's very much possible that one fellow moves here quickly, other fellow moves slowly, like a road. BMW versus Maruti. BMW can always go quickly like that. Maruti will go like this. But here, it's just one line that we are considering. Okay, so in this case, they will go together. And that makes it a very simple problem, part A. I think I will leave part A to you after this point. But I will discuss part B, which should be looking at the numbers. Well, that should also be easy. So what I will do is that I will explain the concept of part B. Then I will ask you which one would you like to take as assignment. Alright, let's discuss what will happen in part B. Mu1 is large, mu2 is small. Clearly, if mu is large, then for an isolated system, A will be small. Rear fellow has large mu, so it will accelerate slowly. Note that in acceleration result, mass doesn't appear. So don't think that it's a big fellow, so it can't go quickly. If mu is small, it will be going more quickly actually. So this fellow will go more quickly, this fellow will go slowly. They will obviously detach. They will become independent from each other. 4 kg going at its own pace and 2 kg going at its own pace slowly. So part B is very easy. It's like two bodies detached and you have to find the acceleration of 2 kg block. Now which one would you choose for assignment so that I can complete the other part right now? Choose the easier one. I think I will delete this working. If you don't choose, then I will make a choice. Comparing the two parts, I think part B is simpler. I think part B will be simpler. So part B is your assignment. And I'm going to complete part A right now. In part A, they will be going together. And therefore, there will be action-reaction forces. But I think I would opt for system as a whole approach, in which case these action-reaction forces won't matter. So let's say this is the system boundary. Then in this direction, (4g) sine 30 well, why not just write 6g sine 30? Then friction. Friction I cannot write as one expression because the two mu's are different. So I will have to write separately, like this. Anything else? Six times A. Now what will be N1 and what will be N2? Mg, which is 2g cos 30. N2, Mg cos 30, 4g cos 30. G is common, which is 10. 6 into half, mu1 is 0.2 cos 30. Root 3 by 2. That is 6a. I have used system as a whole approach here, taking 4 plus 2 as one system. And it can be done because they are going together. They are having identical acceleration, so it can be done. This 10 has already been considered. Now this needs to be calculated. Around 2.7. So that's about part A. So later I realized that part B would be easier, and that's why I'm giving part B as assignment. In fact, it can be told almost orally by inspection, part B, because they are detached. We just have to tell the final answer for part B. No working required. Any questions? Let me know. I think earlier I mentioned this once, that if you take your book and you place it against the vertical wall, obviously the book will fall if you release it. But if you press the book while the book is in contact with the wall, you press the book. Table is nowhere near. It won't fall. You are just pressing the book. You are not giving it a support from the bottom. The book is in contact with the wall and the book is being pressed by you, not supported at its base, but is pressed against the wall, and the book won't fall. Now, what is interesting is that falling of book has to do with vertical force. Gravity is responsible for the fall of the book. Only a vertical force can cancel a vertical force. But when you press the book, you are applying a horizontal force. Fall of book is along vertical direction. So how is it happening that by pressing you apply a horizontal force and a vertical force is balanced? mg force is balanced. And this interesting situation is because frictional force is such a force which is a horizontal force, which can be a horizontal force, but it depends on, if it's horizontal force, it depends on vertical force, and if it is vertical force, then it depends on horizontal force. Frictional force depends on normal reaction. I'm talking about limiting frictional force or kinetic frictional force. Both of them depend on normal reaction. Now, in case of wall, when you press the book, wall book example, when you press the book, you increase the normal reaction, right? And the book is in contact with the wall, and mg is pulling the book down. But when book wants to fall, or when the book is likely to fall, frictional force acts in opposite direction. Static friction does not like net force. mg is the net force acting on the book downwards, and book is in contact with the wall. So between the book and the wall, there is frictional force, and that frictional force does not like mg. So while mg is like this, or rather like this, mg is like this, the static frictional force is like this. It may have some value, may not be enough to prevent the fall, may not be enough, but when you apply more force here, then normal reaction increases. This frictional force depends on normal reaction. It becomes big. Here it goes. If you apply enough force so that the normal reaction is enough, then mu n can become as big as mg, and the book won't fall anymore. Another real life example involving static friction is this. You have got a roller, big roller in front of you. Rollers are used in sports. So that roller has to be used. Would you like to push it like this, push it and move it, or would like to pull it and move it? The only concern here is less effort you want to make. From that consideration, you have to decide whether you want to push it or pull it. Now sometimes one can be afraid that if I'm walking here and I'm pulling the roller, well, it can run over me. Then there can be a security concern. The person may not like pulling at all. Person would rather feel comfortable pushing the roller moving here, the person walking here, safe. That's a different angle to the story. The question here is just thinking about effort, how much effort I have to make. That is the only consideration. Which choice would you make? Pushing the roller or pulling the roller? And physics can answer this question very easily. When you try to push the roller, you are applying force in this direction. The roller has got mg force acting downwards and normal reaction acting upwards. N is up, mg is down. And you are applying force in this direction. Now when you apply force in this direction, your force has got two components, one here and one here. That's how you break a vector, right? This vector can be broken in two components, one to the right, one down. One to the right, one down. The component that you are exerting, horizontal component, that will just try to move the roller in forward direction, which is your intention. Move the roller in forward direction. But what this component is doing, it's like pressing the roller down. This component is pressing the roller down. Whenever you press something down, you increase normal reaction. Whenever you press something down, like you press the book against the wall, you always increase normal reaction. And whenever you increase normal reaction, you increase friction. When you increase normal reaction, you increase friction. That means you are making your own job difficult by increasing friction. You would like no friction, right? Roller can be moved nicely. Now you yourself are increasing frictional force because you are in a way or partly pushing the roller down, thereby increasing normal reaction and hence friction. So that's not smart. Let's understand this case. Pulling the roller. Now when you pull the roller, by applying a force like this, your force can be broken into two components. One component like this, other component like this. Right and up. While right component on the right will move the roller forward, which is what you want, but vertical component will also do something. Vertical component, whenever you lift something up, you reduce normal reaction. Whenever you lift something up, you reduce normal reaction. If a book is lying on the table, you lift it, you reduce normal reaction, and if you lift it a lot, it will come off the table. Normal reaction will become zero. If the book comes off the table, normal reaction between the book and the table becomes zero. So lifting a book away from the table means reducing the normal reaction between the book and the table. That's exactly what you're doing here. A component of your effort is trying to reduce the normal reaction between the roller and the surface. While it's a vertical force, frictional force depends on normal reaction. So normal reaction falls, frictional force falls. and your effort is reduced due to that. So only considering about the effort angle, it is wiser to pull than to push. Any questions? Let me know. I think we can take one more short question. Very interesting one. Suppose a block is kept on a rough horizontal table and it slips under the action of some horizontal force. It slips on the table. Force can be like this. It is slipping. Mu is given as mu. Table refuses to move. This is a very common thing. Like you are moving a book on a table, rubbing a book on a table, dragging it in one direction, and the table doesn't move. Find the total frictional force applied by the floor on the legs of the table. On the legs of the table. So what is the friction between the table and the floor? That's the question. It's a static frictional force that is taking place between the table and the floor. So never write mu n for static friction unless you are sure that it is the case of maximum static friction. That's why question says, do you need friction coefficient between the table and the floor? Or do you need the mass of the table? Some people, when they hear friction, are immediately tempted to say mu n. That's where static friction creates trouble. We don't know if the static friction here is a limiting or not. So it is not safe at all to use mu n formula where n is the normal force between the table and the floor. This is not the correct approach. So what is the correct approach? Static friction is a smart force. It will just see how much is the opposition and it will become exactly equal to that. How much is the opposition? Well, it's sliding. If it is sliding, then the kinetic friction will be mu times this normal reaction. And this normal reaction is equal to mg. So kinetic friction is mu mg, which is acting on this block. Block will also apply an equal and opposite force on the table. And that will be mu mg, but in the opposite direction. Right? Now, table is experiencing mu mg force, but table is not moving. Who is balancing this mu mg force? Vertical forces are different, but who is balancing this mu mg horizontal force? There has to be static friction horizontal force, which is balancing this mu mg. Take table as your system and say that table is not having any acceleration in horizontal direction. So on the table system, net force should be 0. And therefore, Fs must be equal to mu mg. Technically speaking, Fs will act through the legs of the table. If there are 4 legs, it will act at those 4 places. So what I have written is the sum of those 4 forces, Fs1 plus Fs2 plus Fs3 plus Fs4. 4 legs. So do we need the friction coefficient between the table and the floor? No. Even if that was given, it would be of no use. Or the mass of the table. Mass of the table is also not required. If we needed to know the normal reaction here, then that would have been useful. But we don't need normal reaction. We don't need normal reaction between the table and the floor. So most problems that you do, in those problems you don't need table as a system. But in some good problems you do need table as a system. Most of the times you don't need inclined plane as a system. Generally, block as a system is enough. But in some problems, even incline is taken as a system. In some problems, incline can slide. Say, for example, this is a floor, and this thing is kept, not fixed, not rigidly fixed, not screwed or whatever. Just it's placed there. So when the block slides, block will apply some reaction force on this triangle, and that force can accelerate this thing in this direction. So we have not taken those types of problems yet. If this prism is, or this triangle is rigidly fixed to the wall, to the floor, screwed or whatever way, mechanical way, then obviously it won't move. And that's what we have taken as the case primarily. Any questions about this? Let me know. Yes, carry on.
So, in all cases, is it right approach to say that the only difference between the static friction and the kinetic friction would lie in their directions only, and of course the condition that in static it would be at rest and in kinetic it would be at motion, and rest the magnitude would be same of both?
How can otherwise they be the same? What is the formula for static friction? What is the formula for static friction?
So the coefficient of friction into the normal reaction.
Is that the formula for static friction? What is the formula for static friction? Is it mu n? This is what I have been saying since so long. Okay, let me ask others also. Do you think that the formula for static friction is mu n? If you think yes, put a tick mark. Fs. Do you strictly agree with this? If yes, put a tick mark. If no, put a cross. So some have understood, some have possibly not understood yet. This is not the formula for static friction. This is a formula for maximum static friction. There is no formula for static friction. That's how we had to do this problem like this. Static friction is a self-adjusting force. It has no formula. It will adjust according to others. So it is others who decide static friction. Okay, any other question? And by the way, there are other differences also. For example, while doing problems, we take just mu as mu, but actually mu s and mu k, they are not 100% same. So we make an approximation, taking each one of them as mu. But while taking theory, I think I mentioned mu k and mu s. K for kinetic, S for static. The reason is this only, that mu k and mu s don't have to be the same 100%. Yes, anything else?
Sir, what is FS1?
FS1. If there are four legs, then between one leg and the floor, you can call it FS1. Second leg, FS2. Third leg, FS3. Fourth leg, FS4. So Fs will be sum of these four. Yes, anything else? Fine. Assignment has been given. We stop now.